So today's lesson is all about acceleration. You're going to see our objectives. I'm going to want you to be able to define acceleration, calculate acceleration, and be able to graph it versus, so it'll be a like velocity versus time graph instead of a position versus time graph to show acceleration, okay? And then in addition to that, we are going to get several formulas that involve acceleration when acceleration is constant. So we're going to run problems that use time, velocity, acceleration, and displacement in them. So there's like 4 or 5 equations. Okay. To begin, acceleration is the rate of change in velocity of an object. You can solve for it using this equation. And once again, I will write this out in a more visually appealing way. I like to write it acceleration average equals change in velocity over change in time. And if you want to write that out even further, you can say velocity final minus velocity initial over time final minus time initial. I would say they are more likely to give you like initial and final velocities, and usually they'll just give you the change in time. But in case they don't, you can write it like this to solve for the change in time. Here's a practice problem for you right off the bat to use that equation in. A shuttle, that should say bus, not butt. I don't know what a shuttle butt is. Slows down with an average acceleration of minus 1.8 meters per second squared. How long does it take the bus to slow from 9.0 meters per second to a complete stop? Okay, so starting as I always like to start with my knowns, okay? I have an acceleration. It's negative 1.8 meters per second squared, and as you're going to discover, generally speaking, the negative sign means you're slowing down, positive sign means you're speeding up. There are some cases in which that's not the case, and we'll talk about that in just a minute, but generally speaking, deceleration is a negative number. Then we had a velocity initial of 9.0 meters per second, and we had a velocity final. They didn't put it in numbers for us, but they said complete stop, which means 0 meters per second. Okay? And then the variable they want us to solve for is change in time. How long is this going to take? So we do not know this variable. And then the equation we're going to use is, of course, going to be the acceleration equals velocity final minus velocity initial divided by change in time. We're going to want to manipulate this to isolate change in time, since that's the variable we're solving for. So if we multiply by change in time and divide by acceleration, we will discover that change in time is equal to velocity final minus velocity initial divided by acceleration. So now we can use that equation to solve for time. Just gonna make us some room here. So we're gonna plug numbers in. Change in time is gonna be equal to our 0 meters per second minus our 9.0 meters per second divided by our acceleration, which is negative 1.8 meters per second squared, which is awesome because we can see that meters and one of the seconds will cancel, leaving us with a unit of seconds, and that the negatives should also cancel, leaving us with a positive value, which is important because time cannot be negative.
I didn't realize second was the only thing squared. I thought it was like
The whole thing was squared?
Thing was squared, and I was like, I'm left with a meter, which means this isn't right. We're good now.
You're good now. Yep. If the meter was squared, it would also have a squared sign on it. Because the squared is next to the second, it's only the seconds that are squared. So then if we can do 9 divided by 1.8, we can see that the change in time that we should get is 5 seconds, but we need to double check, and this should be 2 significant figures, so we're going to do 5.0.
So, why is acceleration in seconds squared? Like meters per second squared.
Another way of saying it would be it's an increase in 1.8 meters per second every second. That's why the seconds are squared.
So something squared means every of it?
Not necessarily. It just means that we're taking the change in velocity divided by time. So, and since velocity is meters per second, and then we're dividing it again by seconds, the seconds wind up being squared. So,
okay.
If it helps you to think of it as 1.8 meters per second every second, that can kind of help, just so you know that's why there's 2 seconds there.
Well, it's just when I think of it the way you said it, I think of 1 second, because for every 1 second you go X amount of meters.
But that would be velocity. For every 1 second you go X amount of meters is velocity. For every 1 second you increase your velocity by so many meters per second. That's acceleration.
Okay.
All right. Moving right along. Okay. Acceleration has a unit of meters per second, or meters per second squared, what we were just discussing. Okay. And acceleration can be positive or negative. When your final velocity is greater than your initial velocity, the object is speeding up and your acceleration is going to be positive. If your initial velocity is greater than your final velocity, then that object is generally slowing down, which means acceleration is negative. If your change in velocity is 0, then of course no acceleration has taken place. That means your velocity was constant over that time period. There was no change in it. Now, the effects of this can be changed by whether or not one of your velocities is positive or negative. Because remember that velocity is positive or negative based on what direction it's occurring in. So it would be possible for you to have a negative final velocity and a positive initial velocity, where technically final velocity is greater than initial velocity because of the sign, but it's not actually speeding up.
Can you repeat all of that?
I'm going to show you a chart on page 49 of your textbook that will help summarize this.
Okay.
You will logically be able, by looking at your initial and final velocities, you will be able to tell if your object is speeding up or slowing down. The point of this is to remind ourselves that a negative velocity doesn't always mean slowing down, a negative acceleration doesn't always mean we're slowing down, and a positive acceleration doesn't always mean we're speeding up.
The rules of like multiplying, where if it's positive or if it's negative, is the same as like here. If they're matched, it's positive. If they're different, it's negative.
Excellent.
Okay.
We can graph acceleration in a similar way to the way we graphed velocity. So instead of having position on the y-axis, this time we will put our velocity on the y-axis. Which means on a velocity time graph, which will show us acceleration, that diagonal line, which on a position time graph meant the object was moving at a steady speed. On this graph, it means the object is speeding up. And on the on the position time graph that showed us velocity, the horizontal line meant the object wasn't moving. On this graph, it means the object is moving at a constant speed. And you can see that. If you compare it to the x-axis, you can see that this person maintained a 20 meter per second velocity for the duration of that horizontal line. On a velocity time graph, there's no way to indicate direction like there was on the previous one, because a downward line doesn't mean returning to the start. It means that your velocity is decreasing, so you are decelerating. And then that curvy, swoopy line means an increase in your acceleration. You have been in science for a while and reading graphs for a while, so you should be able to read a graph. The biggest and most important thing on a test is to make sure you look at the axes and see what they're labeled. Because I might show you a graph like this with a diagonal line and ask you, what does this line mean? And if you think it's a speed time graph, a velocity time graph, and it's actually a position time graph, what that line means is different.
So this is a velocity time graph, and last time was a position time graph?
Yes. Decreasing acceleration would be curved like this.
Okay.
Yes, deceleration is shorthand for slowing down, because technically speeding up and slowing down are both forms of acceleration, but when we talk about them colloquially, people like to be able to say something different for slowing down, so they say decelerate instead of accelerate. Scientifically, decelerate is not really a thing, but all right. When acceleration is constant, the time interval is going to remain the same, but the distance traveled is going to increase because you're increasing how quickly you cover ground. When acceleration is constant, we can derive a variety of formulas from the acceleration formula. What we're going to do next is I'm going to actually write out how we derived these equations. If you want at the end of the notes to have a comprehensive list of the equations from this section, it's in a box on page 56 of your textbook, just so you have somewhere to find it. We're also going to take them and put them on a note card because you will be allowed to use them on your test. I think we have enough time left in class to get through one of these formulas, so we'll start this today and we'll pick up with it again tomorrow.
Okay.
All right, I'm gonna give myself a blank screen here. Okay. And we're going to start with number 1 being displacement. From acceleration, velocity initial, and time. Okay? So this is the first formula we are deriving, where we can get displacement by having an acceleration, a velocity initial, and a time. We know that velocity average is equal to a change in position, or displacement, over change in time. When velocity is constant, then average velocity is equal to velocity initial plus velocity final divided by 2. It's an average, right? If it's average velocity, then the velocity you started at and the velocity you ended at divided by 2 should get you an average.
So these are all formulas for when acceleration is constant, and this one's saying specifically this one only works when velocity is also constant?
Yes. or at the very least, they're saying that this portion of this formula is true when velocity is constant.
So is that average velocity?
Mm-hmm.
Equals velocity initial plus velocity.
So now we have two equations, this top one here and this bottom one here, where we are talking about average velocity. So we can set these equal to each other. So what that would look like, I'm gonna wipe my screen here. What that would look like if we set them up to be equal to each other is that change in displacement over change in time, as we said, was equal to velocity average, which we also know is equal now to velocity initial plus velocity final divided by 2. Or you can cut out the middleman and you can write So then if we want to use this equation to solve for displacement, all we have to do is multiply both sides times change in time to get the displacement by itself, and the result is the equation change in displacement is equal to 1/2 velocity initial plus velocity final times change in time. So this is our first equation, an equation we can use when acceleration is constant to determine displacement from acceleration, velocity, and change in time. I'm not going to expect you to derive this equation on the test, but I do think that it's worth the time to talk through how we derive the equation, and then we'll go through example cases of how to use it. So, for this first one, here we have our practice problem that goes with it. A racing car reaches a speed of 4.2 meters per second. It then begins uniform negative acceleration using its parachute and braking system and comes to rest 5.5 seconds later. Find the distance that the car travels during the braking. So, things we know. We know that because we are talking about the time during which the car was braking, our initial velocity is what they started at before the braking began. So that 42, not 4.2 meters per second is our velocity initial. We know that it comes to rest, which means that our velocity final is 0 meters per second. And we know that they gave us a change in time of 5.5 seconds. So that's the information we have. And they want us to solve for displacement, which we know we can use this new equation of displacement is equal to 1/2 velocity initial plus velocity final times change in time. So we're going to go ahead and sub in the numbers we know. 1/2 of velocity initial, which is 42 meters per second. I'm going to just leave out the velocity final because we know it's 0 meters per second, so that's not going to affect our end result, and the change in time was 5.5 seconds. So, to do the math, we're just going to take 42 times 0.5, which comes out as 21, and that's meters per second. And we're going to take that times 5.5 seconds, wherein the seconds will cancel and we'll be left with meters. I get 115.5. And of course we have to look at significant figures.
Only 2?
which we can only have 2 of according to the problem. So we're gonna look here and round. So we should wind up with 120 meters.
I need to show my dad this.
He will be not super pleased that we rounded up. But that is how we're gonna do this. Okay, that's where we're gonna stop for today. And we'll pick up with the other, I believe it's 3 equations tomorrow.
This is actually very satisfying, like writing.